Hello everyone and welcome to Calc Lesson number 37. Today we are still going to be analyzing and graphing functions. However, today we're going to be moving on from the polynomial and radical functions we looked at the last couple days. We're going to be moving into rational functions. So as a quick review, the same things we've been looking at, we want to focus on what we can get from our function f of x, from our first derivative f prime of x, and from our second derivative f double prime of x. New with our rational functions is that we can actually find our vertical asymptote or asymptotes from our original function f of x, and then everything else is the same as what we've been doing over the past couple of days. Additionally, with rational functions, we want to focus on end behavior, talking about our horizontal asymptotes or our slant asymptotes. So just a quick review from what you learned in pre-calc. Let n be the degree of the numerator and d be the degree of the denominator. Your horizontal asymptote is then dependent on the relationship between those two degrees. So if the numerator degree is less than the denominator degree, then you have a horizontal asymptote at y equals 0 on the axis. If your numerator degree and denominator degree are equal, then you have a horizontal asymptote at y equals a over b, where a over b is the ratio of leading coefficients of the numerator and denominator. And then if the numerator degree is larger than the denominator degree, you have no horizontal asymptote. But in a very special case, if the numerator degree is greater than the denominator degree by exactly 1, then you have a slant asymptote. And hopefully you remember you have to use long division, ignoring the remainder, in order to find the equation of your slant asymptote. So if you need to pause the video to jot that down on a post-it, make sure you have it so that you can apply that over the next couple of examples. And the directions for these examples for today are the same as they have been for the past couple of days. We're going to analyze our functions by filling in the missing information in the tables that are provided. We're going to show all of our work as we find derivatives, find our critical points and points of inflection, finding our change of sign graphs, and then after we find all of our information, we're going to go ahead and sketch the graph. Okay, so let's jump right in with our first example, f of x equals -3 over x minus 2. Again, just like in the last two, we want to start by finding whatever we can from our original function. So the first thing I want to identify is the domain of this function. Over the past couple of days, our domain has been all real numbers, negative infinity to positive infinity, as we were working with our polynomials and then our cubed roots. Today, we're working with rational functions, and as you hopefully remember, rational functions often have domain restrictions wherever their denominator is going to be equal to 0. So here, x minus 2, if we let that equal 0, we would have a problem. In fact, we would have what's called a vertical asymptote. So the domain of f of x will be all real numbers except for 2. Whoops. And of course, we want to write that in interval notation. Why does my color keep changing? So from negative infinity to 2, and again from 2 to infinity. And I know it's in kind of a funky order, but your vertical asymptote is here at the bottom. We have a vertical asymptote at x equals 2. Again, we still want to keep finding anything we can from our original function before we do our derivatives. So we can still talk about our intercepts just like we did before, setting our function equal to 0 or plugging in a 0. So if we set our function equal to 0, remember we can really just set our numerator equal to 0. -3 equals 0 is never going to happen, so we actually won't have an x-intercept. Plugging in a 0, f of 0, to find our y-intercept, we get -3 over 0 minus 2 gives us 3/2. So we have our y-intercept at the point, so no x-int. Y-intercept is at the point 0, 3/2. And then from our original function, remember we can also identify our end behavior, which would mean our horizontal asymptote or our slant asymptote. So identifying the degree of our numerator as 0 and the degree of our denominator as 1, because the degree of the denominator is larger, we have a horizontal asymptote on the axis at y equals 0. So it makes sense that we don't have an x-intercept. That's everything that we can get from our original function f of x. So now I want to go ahead and take our first derivative. So to find f prime of x, I'm actually going to rewrite my function f of x as -3 times x minus 2 to the negative first power so that I can go ahead and just take this derivative using the chain rule. So taking my first derivative, f prime of x, keeping my negative 3 constant multiple in front, then using the chain rule, I bring down my negative 1, leave my inside the same, take my power to the 1 less, so negative 1 minus 1 is negative 2, and then multiply by the derivative of the inside, which would just be 1. And then of course we just want to simplify that, so I would write this as f prime of x equals negative 3 times negative 1 gives me a positive 3 over x minus 2 squared. And I'm just going to fill that into my table. Okay, from here, just like we did in the last couple of days, we want to find our critical points so that we can identify our intervals of increasing and decreasing and any relative minimums or maximums. So remember, to find our critical points, we set the numerator equal to 0. Doesn't happen. We set our denominator equal to 0, so we have x minus 2 squared equals 0, and we get a critical point at x equals 2. So we can go ahead and set up our number line. And we're testing points around 2. Remember, x equals 2 was our vertical asymptote. So if we test, I don't know, a 0 and a 3 inside our derivative, f prime of 0, numerator is 3 is positive over our denominator is squared is also positive. So we are increasing between negative infinity and 2. And then plugging in f prime of 3, we have 3 is positive over something squared is positive. So we are also increasing after that from 2 to infinity, which means we have no intervals where we are decreasing. Because we don't have any change in increasing or decreasing, we actually have no relative maximums and no relative minimums. So far, not too exciting. From here, we want to go ahead and take our second derivative. Now to do that, I'm going to think about rewriting my first derivative, f prime of x, as 3 times x minus 2 to the negative second power, again, just to make the differentiation process a little bit easier for me. Taking that second derivative, leaving my 3 in front, bringing my negative 2 down, leaving the inside the same, taking my power to the 1 less, negative 2 minus 1 is negative 3, and then chain rule multiplying by the derivative of the inside, which would just be 1. I can write my second derivative, f double prime of x, as 3 times negative 2 is negative 6 over the quantity x minus 2 cubed. Going to go ahead and fill that into my table. Okay, again, I want to set my numerator equal to 0. Nothing happens. Set my denominator equal to 0. And again, we get x equals 2. So it seems like our vertical asymptote is going to be a pretty big piece of our graph. Again, testing around, this time for concavity. So I'm testing in my second derivative. So f double prime of 0 gives me negative 6 is always negative, over 0 minus 2 is a negative, cubed is still a negative, which gives me a positive, meaning I'm concave up from negative infinity to 2. And then f double prime of 3, negative 6 is still negative over, plugging in a 3, 3 minus 2 is 1, cubed is positive, which makes this a negative value, and I'm concave down between 2 and infinity. Now I do have a change in concavity at x equals 2, but because that was my vertical asymptote, I have no point of inflection. So we found all of that information. Now that we have that, I'm going to flip over the screen and we're going to go ahead and sketch our graph. Okay, just like in my last couple of videos, I brought all of our information over and then I just sketched a quick graph. Again, just looking at the numbers that I was going to have to graph, I gave myself just 4 tick marks on each side of my axis. So with my rational function, I'm going to go ahead and start by graphing my vertical asymptote and my horizontal asymptote. I'm going to use a highlighter for mine, but you can go ahead and use a highlighter or a dotted line if that's all you have. So I have a vertical asymptote at x equals 2, so I go over to x equals 2 and I'm going to plot my vertical asymptote. And I have a horizontal asymptote at y equals 0, which is just our x-axis, our x-axis. Okay, so that's going to help me because my vertical asymptote, remember, I'm not going to cross that one. My horizontal asymptote is going to help me to determine the end behavior of my graph. Now I'm going to look at what points are actually on my graph. So I know I don't have an x-intercept, but I have a y-intercept at 0, 3 halves. So at 0, 1 1/2, I'm going to add a point. And that's sort of all I have, right? I didn't have a minimum or a maximum or a point of inflection. So that's the only point I actually have on my graph. Hopefully I recognize rational function usually has several branches. So because I have my vertical asymptote, I'm just going to try to find one more point on one of the other branches. So I'm going to plug in 3 and see what I get out from my original function. I get negative 3 over 3 minus 2. Gives me negative 3 over 1. So I also have the point 3, negative 3, and I'm going to plot that. Because now I feel a little bit better about drawing both branches of my graph. So looking at my increasing and decreasing, I know that I am increasing everywhere, meaning I'm always going to have some kind of positive slope. So that means I'm going to have a positive slope here and some kind of positive slope here. I'm going to be concave up on the left half of my graph from negative infinity to 2. So I'm going to take this and make sure it's curved. And then I'm going to be concave down on the right side of my graph from 2 to infinity. So same idea, going to take this, keeping it increasing, and just make sure it's curved. So now I recognize this as a rational function. I have 2 branches that are going to be approaching my asymptotes. So I'm increasing and concave up on this whole side, and I'm increasing and concave down on this whole branch approaching my asymptotes. Okay, we're going to keep on moving to the next example. Here we have the function x over x minus 1. Again, starting the same way, looking for our domain, our intercepts, our asymptotes. So the domain of this function, again, we want to look at where our denominator would be equal to 0. And we know that we would have a vertical, or our domain cannot be 1. So our domain would be from negative infinity to 1, and then again from 1 to infinity, meaning we have that vertical asymptote at x equals 1. To find our intercepts, remember we're going to set our function equal to 0, setting our numerator equal to 0, we get x equals 0. So we have an x-intercept at 0, 0, which is also going to be our y-intercept. Plugging in our 0, we get 0 over negative 1. Those are our intercepts. Identifying our degree, we have degree 1 in our numerator and degree 1 in our denominator. So we're going to have a horizontal asymptote at that a over b ratio. So our leading coefficient is 1 and 1. So 1 over 1 is just 1. That's everything we get from our original function. Now it's time to take our first derivative. And in order to do that, because we have an x in our numerator and an x in our denominator, we need to use the quotient rule. Hopefully you remember the quotient rule. So to take that derivative, we're going to have our denominator, x minus 1, times the derivative of our numerator, which is just 1, minus our numerator x times the derivative of our denominator, which is just 1, all over the denominator squared, x minus 1 squared. And then I'm just going to simplify that. So this would be multiplying that 1, you get x minus 1 minus x over x minus 1 squared, which we can just write, our x's actually cancel out, as negative 1 over x minus 1 squared. Okay, from here, we want to look for those critical points, which we find by setting our numerator equal to 0. Doesn't happen. Setting our denominator equal to 0. We get x equals 1. Setting up our number line and plugging in to our first derivative to test that sign for increasing and decreasing. F prime of 0, numerator is always negative, denominator is going to be positive. That gives us a negative value. And then f prime of 2, numerator is always negative, denominator is going to be positive, another negative value. So we are decreasing on both of these intervals from negative infinity to 1 and 1 to infinity. Critical point at 1. Sorry, I forgot to fill that in. And we are going to have no intervals of decreasing, just like in the last problem. Oh, hold the phone. I wrote that totally backwards. Sorry about that. We are decreasing everywhere from negative infinity to 1. 1 to infinity, no intervals of increasing, but just like in the last problem, because there's no change from increasing to decreasing or decreasing to increasing, once again, we have no relative extrema. Taking our second derivative, now when I go to take my second derivative, I'm going to actually rewrite my first derivative here as negative 1 times x minus 1 to the negative 2. The reason we're doing that is because I don't have a variable in my numerator, so now I can take the derivative just using the chain rule, whereas earlier when we had that variable in the numerator, we had to use the quotient rule. Taking this derivative, we keep our negative 1 out front, bring down our negative 2, leave our inside the same, make this to the 1 less power, and the derivative of the inside is just 1. So we can simplify our second derivative. Negative 1 times negative 2 is a positive 2 over x minus 1 cubed. Setting our numerator equal to 0, nothing happens. Setting our denominator equal to 0, we get x equals 1. Setting up our number line and plugging into our second derivative. Numerator is always positive. Denominator, we have to plug in. 0 minus 1 gives us a negative cubed stays negative. A positive over a negative gives us a negative value, so we're going to be concave down from negative infinity to 1. Plugging in at 2. Numerator is 2 is always positive over 2 minus 1 is a positive, cubed is still a positive. So a positive over a positive gives us a positive value, meaning we are concave up from 1 to infinity. Once again, we split that at x equals 1 because that's our vertical asymptote. That is not going to be our point of inflection. So we have all of our information. We're going to take this over to the next slide to sketch a quick graph. Okay, just like before, I just sketched a quick axis so that I can go ahead and sketch my graph. I'm using only a few tick marks looking at the values that I'm going to have to plot, not too far out on the axis. So let's start by plotting our asymptotes. Again, I'm going to use a highlighter. You can use a highlighter or a dotted line. Our vertical asymptote happens at x equals 1, so I'm going to add that vertical line in highlighter. And my horizontal asymptote happens at y equals 1, so I can go ahead and add that horizontal line in highlighter. Again, that's just to help me so I know where the branches of my graph are going to be. From here, I'm going to plot any points that I know are on my graph. I have my x and y intercept at the origin 0, 0, so I can add that point. And then because I know that the only value not in my domain is 1, I want to find my other branch. So I'm going to go ahead and plug in something on the right side of my graph. I'm just going to go with 2. So plugging 2 into my original function, I get 2 over 2 minus 1 is 2 over 1. So I have the point 2, 2. And adding that helps me to see where my branches are located. Now I know that I'm decreasing everywhere, so I have to have a negative slope and a negative slope. And then I'm concave down everywhere up until that vertical asymptote. So on that entire left part of my graph, I'm going to dump out that water. And then on the entire left part of my graph, from 1 to infinity, I'm going to hold the water in. So we're decreasing everywhere, but then changing that concavity. So just to finish out my graph, going towards those 2 branches on either side. Okay, our final example for today, we have f of x equals x squared plus 4 over x. So just like always, we want to start by finding what we know from our original function. So looking at the domain of a rational function, we want to know where our denominator is going to be equal to 0. In this case, x cannot be 0. So we're going to split our domain from negative infinity to 0 and 0 to infinity because we have that vertical asymptote at x equals 0. Plugging in to find our x-intercepts and our y-intercepts. X-intercept, you set your function equal to 0. So setting our numerator, x squared plus 4 equals 0. We get x squared equals negative 4, which has no real solution, which means I have no x-intercept. And then to find our y-intercept, we evaluate our function at 0. So f of 0 gives us 0 squared plus 4 over 0, which is not going to happen. So we have no y-intercept. So far, an exciting graph. Okay, from here, I want to go ahead and find our first derivative. You are welcome to go ahead and use that quotient rule in order to find the derivative, but just notice that it is given. F prime of x is x squared minus 4 over x squared. Again, please feel free if you want to pause and try and find it. It'll just be a bit of work for you. From here, we want to find our critical points. So we're going to set our numerator and our denominator equal to 0. So setting that numerator equal to 0, x squared plus 4, setting the numerator of our derivative equal to 0, x squared minus 4 equals 0. So x squared equals 4, so x gives us plus or minus 2. And then also setting our denominator equal to 0, we get x equals 0. So critical points happen at -2, 0, and 2. So we can go ahead and set up that number line. And then we want to test around, so let's test things like -3, -1, 1, and 3. Plugging into our first derivative, f prime of -3 gives us 9 minus 4 is a positive 5 over a positive gives us a positive. F prime of -1 gives us 1 minus 4 is a negative over something squared will always be positive, gives us a negative value. F prime of 1 minus 4 is negative over that denominator is always positive, gives us a negative. And then finally, f prime of 3 gives us 5, which is positive over an always positive, positive. So we are increasing, decreasing, decreasing, and then increasing. Listing out those values, we are increasing from -infinity to -2, and then not again until 2 to infinity. And then we're decreasing in those middle intervals from -2 to 0 and 0 to 2. Looking at those changes, we have a change from increasing to decreasing when x equals -2. That's going to make that a relative maximum. And then we change from decreasing to increasing at x equals 2. That's going to make that a relative minimum. Remember, we always write our relative extrema as an actual point on our graph. So we're going to go ahead and plug in f of -2 gives us -2 squared plus 4 over -2 gives us 8 over -2 is -4. So we have the point -2, -4, and then also plugging in for that minimum at f of 2 gives us 2 squared plus 4 over 2 is just 8 over 2 is 4. So we have a minimum at the point 2, 4. That's everything we can get from our first derivative, so now I want to go ahead and find our second derivative. Again, please feel free to go ahead and use your quotient rule to find your second derivative. However, if you notice, in this case, it was given to you. So our second derivative is 8 over x cubed. We want to find our intervals of concavity, so we're going to set our numerator equal to 0, nothing happens. Setting our denominator equal to 0, we get x cubed equals 0. So x equals 0. We're going to set up our number line. Setting up our number line and testing around, let's test -1 and 1 inside our second derivative. F double prime of -1 gives us 8 is positive over -1 cubed is negative, a negative value. And then f double prime of 1 gives us 8 is positive over 1 cubed is positive, a positive value. So we are concave down from -infinity up till 0, and then we are concave up from 0 to infinity. We do change our concavity at x equals 0, but remember that was our x-intercept, so we have no point of inflection. And my sincerest apologies, I completely forgot to talk about end behavior. So going back to our original function, and we could have done this in the beginning, going back to our original function, we want to identify the degree of our numerator and of our denominator to determine if we have a horizontal or slant asymptote. So in our numerator, we have degree 2, and in our denominator, we have degree 1. Since our numerator has a larger degree, we actually have no horizontal asymptote. However, because it has a larger degree by exactly 1, we do have a slant asymptote. And remember, the way we find that is by doing polynomial long division. So we want to actually divide x squared plus 4 divided by x. So we're going to put x on our outside, x squared, use a placeholder, 0x plus 4. Hopefully you remember doing polynomial long division. We're doing x into x squared. We would need to multiply x times x. I keep everything lined up. Multiply x times x, we get x squared. These cancel out. We have 0x plus 4. That's going to be our remainder, which we can go ahead and ignore. So we have a slant asymptote at the line y equals x. Okay, so let's go ahead, take what we found, and graph it. So just like before, I want to start by adding my asymptotes. So my vertical asymptote happens at x equals 0. So I'm going to go ahead and add that vertical asymptote in highlighter on my axis. Now I don't have a horizontal asymptote, but I do have a slant asymptote, and that slant asymptote happens on the line y equals x. So I'm going to carefully dotted line up y equals x. My highlighter's a little thick on the side. All right, so I have that dotted line for my slant asymptote y equals x, and then I have my vertical asymptote plotted. Actual points on my graph, remember I had no intercepts, no points of inflection, but I do have a minimum and a maximum. So I have a minimum, I wrote them backwards, I'm sorry. I have a minimum, my maximum is at 2, 4, and my minimum is at -2, -4. There we go. I have a maximum at 2, 4, so going over 2 and up 4, and a minimum at -2, -4. So I can see sort of where my two branches are going to be. I know that I'm increasing from -infinity to -2, so I'm going to be increasing this whole way. And then I'm increasing again from 2 to infinity, so in the last part of my graph. I'm decreasing from -2 to 0, and then I am decreasing from 0 to 2. So filling in just my increasing, my decreasing, my slope of the tangent line. From there I want to change my concave up and concave down, so it looks like I'm going to be concave down on my entire left portion of my graph from -infinity to 0. So I'm going to curve my lines so that they would be dumping water. And then I'm concave up on the entire right portion of my graph so I can curve my lines. And then finally, I'm just going to make any last adjustments to make sure that my rational function is approaching my asymptotes, keeping that increasing, decreasing, increasing, decreasing, and concavity. And there's my final graph. Great job today. Homework 37 is another worksheet inside Class Notebook for analyzing and graphing rational functions. You can go ahead and ask your teacher if you have any additional questions.